First, I would like for you guys to open your packets to 5-4. We're going to work problem 5.4. This is below the problem we worked the other day. The question says the tallest and fastest roller coaster in the world is now the Steel Dragon in Japan. The ride includes a vertical drop of 93.5 meters. The coaster has a speed of 3 meters per second at the top of the drop. It says that we're neglecting friction. We want to find the speed of the riders at the bottom. So what I'm going to do is I'm just going to draw a quick picture. It says a vertical drop. I'm going to say that it's a slight angle. So here we go. You're up here, and then all of a sudden you drop pretty steep until you come to the bottom. It says that the height of the drop, so from there to, let's say, the very bottom right here, we'll call that the bottom, that height is 93.5 meters. Okay? And so what we're going to do is we're going to neglect friction, so there's no friction. There is, if that's the case, there's really only two forces that are going to be acting on it. There will be the normal force, which is always perpendicular to the path, and then there's going to be gravity, which is straight down. What I want you to note is that because Fn is always perpendicular to the displacement, okay, because the normal force is always perpendicular to displacement, the work done by the normal force will be zero. There won't be any work done by the normal force. The normal force is a non-conservative force. The only conservative force that we know of right now is gravity. And so what I'm going to do is I'm going to say, all right, work done by a non-conservative force is equal to the change in mechanical energy. We said right now that the normal force is not doing any work. The only force that's really doing any work at all is gravity. So what we're going to do is I'm going to say, hey, work non-conserved is zero. Gravity is the only thing that's acting on it. And so what I'm going to say is I'm going to say, all right, my mechanical energy at spot 1 equals my mechanical energy at spot 2. Spot 1 is going to be the top of this. So here's spot 1 up here. And then spot 2 is going to be the bottom of the roller coaster. Okay, so there's spot 2 right there. And so what I'm going to do is I'm going to say my mechanical energy at spot 1 equals the mechanical energy at spot 2. In other words, as this thing is moving, if gravity is the only thing, remember, gravity can't change me. Gravity can't change me. What I mean by that is not me personally, but me mechanical energy. So because it can't change me, the total mechanical energy will stay the same. In other words, the change in mechanical energy is zero. So what makes up mechanical energy? We talked about this, that mechanical energy is made up of kinetic energy, which is energy due to motion, plus potential energy, which is energy due to position or location. And that is both, so if I want to find the mechanical energy at spot 1, I would take the kinetic energy at spot 1 and add it to the potential energy at spot 1. Then my mechanical energy at spot 2 would be the same thing. It's the kinetic energy at spot 2 plus the potential energy at spot 2. And so here's the thing. Because 2 is the lowest possible spot, this is the lowest in my experiment, I'm going to call that the 0 spot for height. Kind of like we would call the ground traditionally, or typically call the ground the 0 spot, because we're not going to go any lower than that. What that implies is the potential energy due to gravity there would equal 0. Why is that? Because mg times h, but if h is 0, you see that? Then potential energy would be 0. So that's a key idea. Okay, I'm going to go ahead and erase that though. All right, so that's my 0 spot. So I know I have no gravity. In other words, potential energy at spot 2 is 0. So do I have kinetic energy at spot 1? Am I moving? Well, it says that we have a speed of 3 meters per second at the top. So I'm moving. So I have 1/2 times the mass of the roller coaster, v1 squared. v1 is this 3 meters per second. That's my velocity at spot 1. Plus my potential energy. Do I have potential energy up here? Yeah, I have the potential to start falling even more. And so that is mgh at spot 1. So the entire left side of my equation deals with spot 1. That equals my kinetic energy at the bottom. So that would be 1/2 mv2 squared. Because remember, I'm just going to come over here. Potential energy is simply mgh, and that's specifically gravitational potential energy. And then kinetic energy is always 1/2 mv squared. And so I'm literally just plugging in for that. Now make sure I pay attention to subscripts. This entire side is the bottom, and the entire left side is the very top. Now what's really cool is I can divide everything by m. So if I divide everything by m, then every term will cancel out. At least the m will cancel out. Then I'm going to multiply everything by 2. Just to get rid of the 1/2. So 2 times the 1/2, so if I multiply that, that just becomes v1 squared plus 2 times gh1, so 2gh1 equals v at spot 2 squared. Well, I know this. It's 3 meters per second. I know the height that's 93.5 at spot 1 relative to spot 2. Because remember, we arbitrarily choose that. And then V2 is what I don't know. So let me come over here just a little bit. I'm going to rewrite this as V2 is equal to V1 squared plus 2G H1 and then square rooted. So I'm ready to plug in. That's 3 meters per second. That's my velocity at spot 1. I square that. Plus 2 times gravity, which is 9.8 meters per second squared, times my height of 93.5 meters. And then I square root that entire thing. So if I do that really quickly, I get 3 squared plus 2 times 9.8 times 93.5. And I get an answer of 1,841.6. Then I need to take the square root of that. So square root that answer. And so I get an answer of about 43. It's 42.9. I'll go ahead and write that, 42.9. Now look at my units. I get a meter per second that's squared. So my unit is a meter squared over second squared. Then that's a meter per second squared times a meter, which is going to be a meter squared over second squared. But then when I add those together, I'm going to get meter squared over second squared, and then I square root them to get just meter per second. So that is actually my speed at the bottom if we assume that we have no friction. And we know that because the normal force is always perpendicular to displacement. Because remember, what's perpendicular mean? It would be the normal force times delta x times cosine of the angle between it. But that angle would be 90 degrees. And remember, cosine of 90 is 0. So the no work is done by a perpendicular force. All right, so now looking at part B. It says find the work due to non-conservative forces on a 65 kilogram rider during the descent if the actual velocity at the bottom is 41 meters per second. Now there's a couple ways we're going to do this, but I'm just going to start with the easiest way. So we're just going to say work done by a non-conserved force equals the change in mechanical energy. All right, so I'm basically finding the work due to non-conserved forces. What could be those non-conserved forces? Air resistance and friction here, more than likely. So what's a change in mechanical energy? That means my mechanical energy final minus my mechanical energy initial. That's my change in mechanical energy, because work can change me. Work done by a non-conserved force can change me. And so how do I find my mechanical energy final? Well, the mechanical energy final is the kinetic energy final plus the potential energy final. Okay, that's mechanical energy final. Minus mechanical energy initial would be my kinetic energy initially plus my potential energy initially. Now, what we did was this is at the top, or what we called spot 1, and that spot right there is at the bottom, or what we called spot 2. So spot 2. It doesn't matter what the subscripts are. You could say this is kinetic energy 2 plus potential energy 2 minus kinetic energy 1 plus potential energy 1. Either one is fine, but I'm just going to go ahead and do this. So do we have kinetic energy at the bottom? Yes, it's 1/2 mv final squared plus potential energy. Well, if we're going to still call that the 0 spot, there's 0 final potential energy. My initial kinetic energy would be 1/2 mv1, or v initial, v1 is also fine, squared, and then plus mgh1, or initial, and that's what would be my potential energy. So there's my potential energy, this is my kinetic energy. So now I'm ready to plug in. It says a 65 kilogram rider, so 1/2 65 kilograms. My velocity is 41 meters per second at the bottom, so 41 meters per second. I would then square that, minus 1/2 65 kilograms times my initial velocity, which was 3 meters per second, because that was my velocity at the top, squared, plus 65 kilograms times 9.8 meters per second squared, times my height, which was 93.5 meters. And so if I do all of that, okay, so I'm going to do 0.5 or half times 65 times 41 squared minus 0.5 times 65 times 3 squared, and then minus 65 times 9.8 times 93.5. And so I get a negative 5,219.5 joules is the work done by non-conserved force. Now the negative sign comes from the fact that energy, remember if we get a negative work, that means energy is taken away from the system. And we would expect energy is taken away because friction is doing work, because we would expect our final speed to actually be 42.9 without the presence of friction. But in reality, it was 41 meters per second with it. So we would expect that to be a negative sign for that. All right. So now what I'm going to do is I'm just going to take a couple minutes and set up your homework problems. So this is question number 2 on the next page. It says, consider a 64 Newton object. So right now we know it's a weight. F sub g is 64 newtons. If I wanted to find the mass, remember mass would be the weight divided by gravity. And you're at a height of 10 meters above a concrete floor. From energy considerations, this is from energy considerations, find its velocity and impact after dropping the object from that height. So here's the thing. If I drop it, the only thing acting on it is gravity, and gravity cannot change me. So the work done by a non-conserved force is a change in mechanical energy. We know that gravity can't change me. That's the only thing that's able to do work. So there's no non-conserved forces. We're going to assume air resistance is negligible. That means my mechanical energy at the top equals my mechanical energy at the bottom. How many forms of mechanical energy do I have? I have kinetic energy at the top plus potential energy at the top equals kinetic energy at the bottom plus the potential energy at the bottom. Well, I would consider that if we're a height, here we go, here's our object, I would call this the h equals 0. So that is 10 meters. This object just sitting there dropped from rest means that the velocity at that spot would be 0. So that means kinetic energy 0. And that at the very bottom, at our second spot, so this is spot 2 and this is spot 1, we have no height, which implies that my potential energy is 0. So basically I'm going to plug in and I'll be able to get my information. Then it says using the calculations from free fall. So remember, we would use our formulas. We would call down to be positive. We know that the initial velocity is in the y direction 0. We know that the delta y is a positive 10 meters. And we know the acceleration in the y direction is a positive 9.8 meters per second squared because we chose down to be positive. So you know 3 pieces of information. You know the acceleration is constant, and so you can use kinematics. So prove that through kinematics. The next one is question number 4. You have a roller coaster. It says a roller coaster ride at an amusement park lifts a car of mass 700 kilograms to a point. So basically it's doing work to give it energy at spot A. It says A is a height of 90 meters above the lowest point on the track as shown above. The car starts from rest, which means my velocity at spot A is equal to 0. So you know if my velocity there is 0, then it means my kinetic energy is 0. And so I think it makes sense for us to call this h equals 0, this dotted line right there, call that h equals 0. It says the cart starts from rest at A, rolls with negligible friction down the incline, and follows the track around the loop of radius 20 meters. Point B, the highest point of the loop, is a height of 50 meters above the lowest point on the track. So then what you need to do is you need to indicate on the figure where you're going to be moving the fastest. Now think about this. Where would you be moving the fastest? You would have to have kinetic energy be in a maximum. When is kinetic energy a maximum? Think about that, because the work done by non-conserved forces here is 0. We're basically expecting that friction is negligible, and the only other force that would be acting on is the normal force, but the work done by the normal force will be 0 because the force normal is perpendicular to my displacement, so it can't do work. So then calculate the maximum speed using work non-conserved equals a change in mechanical energy. You know the non-conserved work is 0, so you can start there. And then you need to calculate the speed VB of the car at point B, knowing the fact that it's 50 meters above. So here's the thing, B is still lower than A, so you would expect this to be some velocity. So some velocity at B is something, because the potential energy at B is less than the potential energy at spot A, and nothing can take energy away from the system in terms of mechanical energy, because gravity is the only thing that's able to do work here. There's no non-conserved forces acting here. So try these 2 problems. If you have questions, come see me for help session.